Welcome to our teacher Taylan Demir's conversation titled Asymptotic Analysis of Fractional Derivatives and Applications, which is the last conversation of today. Teacher Taylan, welcome to you too. I hope you are fine. Would you like to introduce yourself?
Yes, thanks. I am Taylan Demir. I graduated from Atılım University at Bachelor of Science program in 2021 at the Department of Mathematics, and later I started to study Master of Science program in Çankaya University. I studied with two different professors, Professor Dimitri Balan and Professor Fatih Çarat, and I studied about fractional calculus and applied mathematics. And later, I graduated from Master of Science program in Çankaya University. I am PhD student at Ankara University now. My field of interest, applied mathematics, mathematical physics, engineering problem, and fractional calculus and their applications in real world problem. My presentation is related with the asymptotic analysis of fractional derivatives and applications. This study is important to understand more better theoretical framework of fractional calculus, and this chapter is related with the application of fractional calculus in the real world problem. And I will explore fractional calculus with some different fractional operators. For example, Caputo fractional operator, Atangana-Balani fractional operator, and Riemann-Liouville fractional operator. For analysis delves into the asymptotic convergence, existence, and uniqueness theorems, providing a rigorous foundation for understanding the asymptotic stability of solutions. Furthermore, we examine applications in various fields where fractional derivatives provide a robust framework for modeling phenomena with anomalous diffusion or memory dependence. The findings offer significant insights into the qualitative behavior of solutions and establish critical criteria for applying fractional models to complex real-world systems. We need to some basic informations to understand this concept. For example, we need to know fractional derivatives, asymptotic analysis, long-term dynamics, fractional differential equations, boundary value problems, non-locality, memory effects, stability criteria, asymptotic convergence, existence and uniqueness theorems, and anomalous diffusion, memory dependence, fractional calculus, and their applications. And now, fractional calculus came from the 16th century. In 16th and 17th century, Gottfried Wilhelm Leibniz developed in normal integer calculus, and later fractional calculus was developed after they had been developed in normal integer calculus and their application in physics. And there are several different from the integer order calculus and fractional order calculus. Integer order calculus can typically can be used with the physics problem, engineering problem, and mathematical physics problem. And fractional calculus gives more flexibility and more accuracy result when we apply this concept on complex systems, where memory and short memory and long-term memory principle. The origins of fractional calculus can be traced back to the works of mathematicians such as Leibniz and Euler, but it has gained substantial momentum in recent decades due to advancements in both theoretical understanding and computational techniques. Fractional derivatives are used with various approaches, which include the Riemann-Liouville's and Caputo's definitions, each offering distinct advantages depending on the application. And later, this concept had been developed between 16th and 18th century. In 19th century, Joseph Liouville used himself definition for formalize the theory, introducing fractional integrals and derivatives into mathematical analysis. His work was extended by Bernard Riemann, leading to the creation of the Riemann-Liouville fractional operator, a cornerstone of the field. And in the 20th century, saw significant advancements. For example, Paul Levy and Michele Caputo and other scientists developed and worked details on this concept as theoretical framework and application on other fields of the science. And Michele Caputo created to Caputo fractional operator, Caputo fractional integral. And he worked with the Mobua Fabrizio, who is Italian professor, and they developed another definitions of the fractional calculus. For example, they used Caputo Fabrizio fractional operator and Caputo Fabrizio fractional integral to solve basic problem on the biological problem, control system problem. And we will introduce later this chapter. And modern development and applications, fractional calculus gained prominence in the late 20th and early 21st centuries. It was applied many fields of science, for example, physics, to modeling anomalous diffusion, quantum mechanics, and material behavior. It was applied and now it has been applying on engineering problem to design of fractional order control systems, viscoelastic materials, and signal processing. And this concept was used with the biological problem, for example, cancer model, and optimal control and PID control to analysis of biological rhythms. And it was applied on the neural science with artificial intelligence field. And beside of this, fractional calculus are be able to used on finance and geophysics fields. And in the prominent scientists in fractional calculus was worked by Igor Polyubny, and Igor Polyubny used numerical methods for fractional differential equations, and he authored the influential book Fractional Differential Equations, which serves as a foundational reference for researchers. And Dimitri Baleanu was my supervisor, my master thesis supervisor. He renowned for his interdisciplinary work. He has applied fractional calculus to diverse areas, including physics, engineering, and biology. He has also co-developed novel fractional operators, such as Atangana-Baleanu fractional operator. And Atangana operator was developed by the Abdon Atangana. And he is a professor at Free State University. And he is a leading figure in applied fractional calculus. And he introduced the Atangana-Baleanu fractional operator, which uses 9 singular kernels for modeling memory effects. His contributions are significant in geophysics, fluid dynamics, and epidemiology. And later, Bruce G. West is known for his work on fractional models of biological systems. West's research connects fractional calculus to complex systems theory. And Mark Mirschahert focused on fractional calculus in hydrology and geophysics. He has made significant contributions to the application of fractional differential equations in natural process. And Michele Caputo is the creator of the Caputo fractional derivative, Caputo fractional integral for differential equation. And his work is foundational in using fractional calculus for modeling physical systems. And later, Francesca Mainardi, he is Italian professor, and he is an expert in fractional viscoelasticity and wave propagation. Mainardi has contributed extensively to theoretical and applied research. These scientists, among others, have expanded the boundaries of fractional calculus, transforming it into a vital tool for understanding complex systems in modern science and engineering. Atangana-Baleanu operator is a modern development in fractional calculus, who introduced by Abdon Atangana and Dimitri Baleanu. This operator has gained considerable attention due to its innovative approach to modeling systems with memory and hereditary properties, especially in fields like geophysics, fluid dynamics, and epidemiology. And in the background and motivation, classical fractional derivatives such as Riemann-Liouville and Caputo derivatives rely on singular kernels. For example, power law kernels, which exhibit strong memory effects. While effective for many applications, these kernels often lead to mathematical complexities and challenges in modeling real-world systems, where memory effects decay or behave differently over time. To address these limitations, Atangan and Balani proposed a new operator with a non-singular and non-local kernel, offering a new, more flexible and accurate approach to modeling phenomena where the traditional power law behavior of memory does not apply. Mathematical definition. This is the Atangana-Baleanu derivative, fractional derivative. We know the E sub alpha is the metric letter function. P alpha is a normalization constant ensuring dimensional consistency. But alpha defines between 0 and 1 open interval. And it is a continuous function, differentiable function. And it replaces the power law kernel with a more generalized and smooth kernel. And what is this non-singular kernel? Unlike traditional kernels, t minus tau power minus alpha, the metric letter kernel used in the Atangana-Baleanu operator is smooth and non-singular kernel, avoiding the divergence issues of classical kernels. Memory and non-locality kernel asks the operator to retain the essential memory property of fractional calculus, but allows for more flexibility in describing memory decay and hereditary effects in complex systems. And we know that the operator has been particularly effective in describing nonlinear systems where traditional fractional models may fail to provide accurate or stable solutions. Therefore, definitions of fractional operators are given places to more accurate results from the simulations when we will apply this concept on the real-world problems. And geophysics. Atangana-Baleanu operator used with the transformative in modeling natural phenomena with complex memory effects. And one professor worked on Atangana-Baleanu fractional operator with geophysics problem in his PhD thesis. And therefore, this is the very important to interpretation wave behavior and ground wave, seismic wave behavior easily. So at this point, Atangana-Baleanu operator give flexible and more accurate results for obtaining the behavior of the seismic wave according to time. And in groundwater flow in fractured rock aquifers, groundwater systems often exhibit anomalous diffusion due to heterogeneous geological structures. Traditional models struggle to capture these irregularities. The Atangana-Baleanu operator, with its flexible kernel, provides an accurate representation of subsurface flow dynamics, addressing issues like delayed response times and non-uniform propagation. In geophysical systems, when I will look seismic wave propagation, I want to say seismic waves can experience memory effects due to viscoelastic properties of the Earth's subsurface. Atangana-Baleanu operator develops of the predictions of wave attenuation and earthquake and dispersion, which are crucial for understanding earthquakes and subsurface exploration. And it can be used to fluid dynamics, where interactions between molecules and external forces often lead to non-classical behaviors the Atangana-Baleanu operator shines. And we can apply anomalous diffusion in fluids and heat conduction with time-dependent properties. Because why we can use anomalous diffusion in fluids? Because this operator is adept at describing particle motion that deviates from classical Brownian motion, such as subdiffusion in highly viscous fluids or superdivision in turbulent environments. And why we can apply fractional Atangana-Baleanu operator on heat conduction with time-dependent properties? Because traditional heat conduction models governed by Fourier's law fail in materials where thermal conductivity changes over time or exhibits memory effects. And in epidemiology, Atangana-Baleanu fractional operators and other definitions of fractional operators can be adapted on this problem. And we know that fractional calculus has found a significant role in modeling the spread of disease, especially when historical infection rates influence current dynamics. And I want to say disease, spread of disease affect population of people. For example, COVID-19 spread affect to population, human populations in all of the world. Therefore, at this point, spread of the disease, affecting on the human population are interpretation with the Atangana-Balano fractional operator according to the time. And during the COVID-19 pandemic, the Atangana-Balano fractional operator was built to model infection curves, taking into account contact rates, interventions, and memory effects in transmission dynamics. Unlike classical models, this approach integrates long-term effects of social distancing or immunity decay, leading to more realistic predictions. And we can use the evolution of epidemics. For example, this operator allows for the inclusion of time-varying parameters, such as transmission rates or recovery times, providing a more nuanced understanding of how disease evolve under different scenarios. And we can use the control systems, Atangana-Balano Caputo fractional operator together can be used to model control system model. And now I am working on the proportional integral derivative control with Caputo fractional operator with my professor Dimitru Balanu and other co-authors to publish new article about this. And in fractional order controllers systems requiring precise adjustment over time, such as robotics or automation, benefit from the Atangana-Balano operator's ability to incorporate memory effects. And tuning and adaptation fields, we can use this concept because it can adapt more efficiently to changing conditions, making them ideal for dynamic environments like power grids or autonomous vehicles. And advantages over traditional operators, especially real-world alignment. The multi-clever kernel's flexibility ensures better alignment with empirical data, especially for processes where memory effects deviate from simple power law behavior. And enhanced mathematical stability are another advantages over traditional operators because non-singular kernels eliminate the computational instability associated with singularities in classical fractional derivatives. Other advantages is versatility across domains because the operator's adaptability makes it suitable for a wide range of problems, from time-dependent boundary conditions in engineering to adaptive models in finance and economics. And limitations, analytical complexity, the involvement of the multi-clever function, while advantages complicates the derivation of analytical solutions. Most real-world applications require advanced numerical techniques, which can be computationally intensive. And other issue is the sensitivity parameters. Alpha is a fractional order variable order derivative in fractional calculus, and alpha is defined between 0 and 1. Its normalization constants in the Atangana-Balano operator need careful tuning, and its small changes in these parameters can lead to significant variations in model outputs, making parameter estimation a critical but challenging task. And later in this chapter is about simulations of geophysics, groundwater flowing fractured rock aquifers, especially Atangana-Balano fractional differential equation is here, and we model typically involves fractional diffusion equations that capture the anomalous diffusion. So we adapted this concept on groundwater flow in fractured rock aquifers. We know that the U function is the groundwater concentration at position x and time t, and this is the diffusion coefficient. Alpha is the fractional order of the Atangana-Balano operator, and alpha is between 0 and 1. And f function is a source term that accounts for external influences like recharge or extraction. In geophysics area, can use this model and the general equation governing seismic wave propagation in a viscoelastic medium with memory effects can be written as is here, and it can be used with seismic wave propagation with memory effects for geophysics. And U is represents the displacement caused by seismic wave at position x and time, but this derivative is not fractional order derivative. We use the normal integer order partial derivative, but alpha is a fractional order. Alpha is defined between 0 and 1. And we know that the U is a continuous function. But rho is the density of the medium. Mu is the elastic modulus. And V is a parameter controlling the memory effects in the medium. Alpha is the fractional order as described by the Atangana operator. This equation allows for a more accurate simulation of seismic wave propagation by including the memory effects which are critical in real-world scenarios. And this is the simulation of the above the equation, seismic wave propagation. Groundwater flow in fractured rock behavior simulation. But if we choose time is equal to 0, 1.01, 2.01, 3.02, and 4.02, according to the time, graphical behavior are different according to time. And simulation output is a plot showing the evolution of groundwater concentration over time. And fluid dynamics. This formulation can be used to model the memory effects and non-local interactions in such systems. For example, capturing anomalous diffusion in fluids with complex interactions for more understanding fluid dynamics. This is the general form. Similarly, U is the concentration of particles at position x and t. And D is the diffusion coefficient. Alpha is the fractional order of the Atangana-Balyan operator. Typically, 0 is less than or equal alpha and less than or equal 1. Maybe alpha is integer or not. And F is the source term, optional, representing external forces or interactions. And this is another model. This model is about the modeling heat conduction in materials with time-dependent thermal properties. And similarly, according to this third equation, U is the temperature distribution in the material, and kappa is the time-dependent thermal conductivity. X is the spatial position, T is the time. And when incorporating the Atangana-Balyan operator, the fractional heat conduction equation becomes here. And where alpha is the fractional order of the Atangana-Balyan operator and the memory effects of the material are modeled. This is the simulation. First simulation is anomalous diffusion in fluids, and other simulation is heat conduction with the with time-dependent thermal properties. And anomalous diffusion, the plot shows how particle concentration evolves over time, with time anomalous diffusion behavior reflected in the speed. And other simulation heat conduction, the plot shows the temperature distribution in the material with time-dependent variable. And according to time, the graphical curvature are different. And Atangana-Balyan operator can be applied in epidemiology to model the spread of infection disease by incorporating memory effects and dynamic factors like varying infection rates, immunity loss, and the impact of the control measures over time. For example, our model is the fractional susceptible, infected, recovered model equations. We use the some constants to establish which is commonly used model for infectious disease is the SR model, susceptible, infected, recovered model. And we know that S is the susceptible population at time t, and I is the infected population at time t, and R is the recovered population at time t. And beta is transmission rate, can vary with countermeasures, and gamma is the recovery rate. And at this point, this is the Atangana-Balyan fractional derivative operator with alpha is between 0 and 1. We know that. And the fractional derivative introduce memory effects, meaning the current rate of change depends on not only on the current state, but also on the history of the system. This is the fractional SR model with the Atangana-Balyan operator. According to the susceptible, infected, recovered, blue curvature is susceptible behavior, and green curvature is recovered behavior, and rat's curvature is the inflected behavior. And this simulation comes from this model. But we can choose another model, not only Atangana-Balano fractional operator, but also Caputo fractional operator, Caputo-Fabrizio fractional operator can be adapted this model. And there are several articles was prepared with Caputo-Fabrizio, Atangana-Balano by Professor Dimitru Balano, Ali Akgül, Aaron Fernandez, and other scientists. They developed, used other definitions from the fractional calculus to adapt the susceptible inflected recovered model. But we say Atangana-Balano give more flexibility results, but other types of model can be used to interpretation SR model. And Atangana-Balano fractional derivative is important, so I want to give this information. And mathematical framework for fractional PID controller. This is the PID control model. And this PID control shows us some constant. For example, kappa p is the proportional, kappa I is the integral, and kappa d is the derivative gains. And my master thesis is about the Q fractional proportional derivative and Q Laplace transforms, but I interpretation only theoretical parts. But we can use Q calculus to model mathematical framework for fractional PID controller. We can use. But this model is only PID controller, and Atangana-Balano operator was used. But I used Caputo fractional operator on my model when I studied on Master of Science thesis in Shanghai University. Now, it is the error signal difference between desired and actual values. And I said kappa, and this derivative operator is Atangana-Balano fractional integral with order alpha. We can use I symbol instead of D. Not important, doesn't matter. But this is the beta order fractional derivative, Atangana-Balano derivative, according to this model. But I want to say alpha and beta is defined between the 0 and 1. Alpha and beta may be 1, but never greater than 1. Atangana-Balano operators enables fractional integration and differentiation, improving system response by incorporating past states into the control signal. This is the simulation according to the system output blue line. Red line is the control signal, and a green piecewise line is the set point according to the fractional PID controller with Atangana-Balano operator simulation. And we wrote detail about this simulation. Yes, and advantages over traditional operators. Real-world alignment, mathematical stability, versatility, limitations, and complexity in analytical solutions and parameter sensitivity are the key advantages over than other traditional operators such as Caputo and Riemann-Liouville operator. Importance and relevance of fractional derivatives are related with my presentation. And the importance of fractional derivatives lies in their ability to model phenomena that exhibit anomalous behavior, which cannot be accurately described by classical integer order models. In fields such as physics, biology, engineering, and finance, systems often demonstrate properties like long-range dependence, non-local interactions, and memory effects. These characteristics can be effectively captured using fractional calculus, leading to more accurate predictions and deeper insights into the dynamics of complex systems. Recent applications have emerged in diverse areas, including viscoelastic materials, diffusion process, signal processing, and control theory, highlighting the versatility and relevance of fractional derivatives in both theoretical and practical contexts. This is this chapter is important to interpretation, more understand advantages of another traditional operators. And we use the asymptotic analysis of fractional derivatives in the next chapter. But we know that the existence and uniqueness theorems to better understand and for addressing the theoretical aspects that ensure the reliability of solutions to fractional problems. And we need to use stability analysis for focusing on the conditions under which fractional systems exhibit stable behavior in this presentation. And asymptotic analysis using real-world examples and implications in various disciplines. Finally, the conclusion will summarize the key findings and suggest avenues for future research in an evolving field. But previously, I wanted to give presentation about the Caputo fractional operator and Riemann-Leibovitch fractional operator before the asymptotic analysis of fractional derivatives. And this chapter is important in this presentation. And Caputo and Riemann-Leibovitch was worked many scientists in the applied mathematics field. And fractional calculus extends the classical concepts of derivatives and integrals to non-integer orders, allowing for more nuanced mathematical modeling. And this is the Riemann-Leibovitch fractional derivative. And alpha is greater than 0, non-integer order. And ft is a continuous function and differentiable function where n is equal to alpha, bar and smallest integer greater than or equal to alpha. R is the gamma function. This definition is about the Riemann-Leibovitch derivative. And Caputo derivative is here, and f to power n denotes the integer derivative of f. The Caputo derivative is often preferred in applications because it allows initial conditions to be specified in a manner similar to classical derivatives. What is the difference between Riemann-Leibovitch, Caputo, and Atangana-Balano fractional derivative and fractional integral? Fractional derivatives and integrals generalize classic calculus concepts, allowing non-integer orders of differentiation and integration. The Riemann-Leibovitch and Caputo and also Atangana-Balano formulations differ in definitions and applications and mathematical properties. Fractional integral is important to understand fractional calculus. And this is the Riemann-Leibovitch type fractional integral. And similarly, we use the alpha is fractional order. And this is the fractional order derivative according to the Caputo derivative. And alpha is between n minus 1 and n. N is higher order. And properties, the Riemann-Leibovitch derivatives is based on the classical integral definition. It requires a function to be defined on 0 and t closed interval and often assumes non-zero initial conditions. And Caputo fractional derivative is here. Similarly, alpha is between n minus 1 and n. And we modify the Riemann-Leibovitch approach by applying the integer order derivative first, then the fractional integral is here. And properties requires ft to be differentiable n times. And second rule is handles initial conditions in a physically meaningful way as they can be expressed in terms of integer order derivatives, f0, f prime 0, point, f power n minus 1, 0. Applications I said in this previous chapter. Similarly, besides of this Atangana-Balano fractional operator, we can apply Caputo Riemann-Leibovitch fractional operator on engineering, physics, and biology due to its compatibility with initial and boundary conditions. Properties from the Atangana-Balano fractional derivative. This is the Atangana-Balano fractional derivative. E sub alpha is the metric level function. B alpha is a normalization of the constant. And we know from this operator E sub alpha is the kernel E sub alpha is non-singular and E sub alpha is metric level function, which avoids the divergence issues near t equals 0. Incorporates memory effects in a smoother way than Riemann-Leibovitch or Caputo derivatives. Applications, we use the anomalous diffusion with scholastic materials and systems with memory effects easily as real-world scenarios. And now, this chapter is about the properties of fractional derivatives. It has a non-locality property. For example, it unlocks integer order derivatives. Fractional derivatives consider the entire history of the function, leading to non-local behavior. These are linear operators, and these linear operators was used with several articles which is published. For example, we can interpret it with the and relate it with the conformable derivative. But conformable derivative is different. But it is not. It was not included in my presentation. Maybe next workshops I can give a presentation about the conformable derivative. Linear operators. This derivative has linearly properties. For example, if you have a possible two derivative alpha order between the summation AF plus BG, we can use the piecewise of the F alpha order derivative and G alpha order derivative, and A and B is the constant of the function. And it has a composition rule. For example, for integer orders, the composition of derivatives is straightforward. However, for fractional orders, the composition becomes more complex, which can be used to analyze the properties of fractional differential equations. It has initial conditions, properties. The formulation of initial conditions in fractional calculus often requires additional consideration compared to integer order calculus, particularly when using the Caputo derivative. And mathematical formulations and notations, we use the d power alpha of ft as a common notations for the fractional derivatives, and I power alpha is a fractional integral. And gamma function and other special function, beta function has important role to definitions of fractional operators. We use the gamma function to interpretation fractional derivative and fractional integral. But I did not give about the beta function because beta is another detailed information about the fractional calculus. But I only focus on the specific information from the fractional calculus in my presentation. And fractional differential equations is another form, is a seventh part. And this is the general formulation. Alpha and beta, other types of the order of the fractional derivative. And white is the unknown function. And F represents a function involving both y of t and its derivatives. Now, actually, this is my other main presentation topic, because I'm focusing on the asymptotic analysis of fractional derivatives, but I need to give information about the basic information of fractional calculus, because it is important. And definition of asymptotic analysis. This method studies the behavior of functions as they approach a certain limit, often simplifying complex systems such as differential equations. This is the formal definition. When x approaches a, f divided by g function gives us a 1. F is asymptotically equivalent to g of x function. Its significance, asymptotic analysis is critical for gaining insights into the behavior of solutions, especially in differential equations where exact solutions are challenging. And there are other key concepts from this chapter. For example, convergence, stability, and decay rates. If we give mention about pointwise convergence, we need to know f of x is a sequence and it converges to a function pointwise. If for every x limit n approaches infinity, f sub n x equal f of x function. This is the uniform convergence formulation, if this form. And stability is another topic from asymptotic analysis. It often analyzed using Lyapunov functions. Lyapunov's theorem, as for a dynamic system defined by x dot prime equal f of x, if there exists a Lyapunov function v of x such that if v of x is greater than 0 for all x to 0, v of 0 is equal 0, and v x equal del operator v times f of x less than 0, near 0, then the equilibrium at 0 is asymptotically stable. And otherwise, it is not asymptotically stable. It is unstable. Decay rates, this describe the rate at which solutions convert to zero based on the structure of the differential equation. And if we give a mention about the exponential decay and R modulus, xt equal x sub 0 times e power minus lambda t. And if the solution converges to zero exponentially, it can be expressed as this here, and lambda is positive. And this is the polynomial decay. X of t equals c divided by t power k, but we know that the c and k are positive. Another mathematical formulation from the fractional differential equation is here. Q is the fractional order, and t is positive, and q is between 0 and 1. This is the Caputo fractional differential equation. And we need to look at the existence and uniqueness to solve, depending on the properties of fractional differential operator and initial boundary conditions. But it's necessary, we need to look initial value problem. And if we assume d power q y of 0 is equal to y sub 0, and d power n minus q y of 0 equal to y sub s 0 and n, where n is the integer part of the derivative, and y sub 0 and y sub 0 and n are constants. And if we look at the boundary conditions, we say in engineering applications, these conditions are often Dirichlet boundary conditions, it necessary fixed values, or Neumann fixed derivatives boundary conditions. And other techniques of force asymptotic expansions, series expansions on my presentation. This series, or Taylor series, is an example of the series expansions. And a function f of x can be expanded around x sub 0 as this form. And asymptotic series is shown in 11th part, and where phi sub n represents functions that exhibit the asymptotic behavior f of x as when x approaches a. And regular perturbation methods. Perturbation methods, other steps to interpretation of the asymptotic analysis of fractional differential equations as Caputo type. For parameter epsilon, solutions are expressed as y t epsilon y sub 0 equal y sub 0 t plus epsilon y sub 1 of t plus epsilon square y sub 2 t plus point. And it is necessary of the use in cases requiring boundary layers and rescaling in singular perturbation. And another this method is the boundary layer theory in regions with repeat changes and boundary layer variable like, and it is introduced and matching conditions are applied between inner and outer solutions. And this is the another model, fractional differential equation model, according with the y of 0 and y sub 0. And d power q is the Caputo fractional derivative. We need to look existence and uniqueness in fractional differential equations. When I research on asymptotic analysis of this model, we need to use Lipschitz condition. Lipschitz condition are important to existence and uniqueness theorem. And Picard iteration method, another method to interpretation existence and uniqueness theorem. And we know that the f function ft y sub 1 minus ft y sub 2 in this absolute value less than or equal L times y sub 1 and minus y sub 2 absolute value. And y functions are unique solution of the fractional differential equation exists. And this is the Picard iteration method in the 12th form. And similarly, I used the fractional integral term to interpretation fractional Picard iteration method to be better understand to asymptotic analysis. And if you look at the numerical methods for fractional differential equations, we need to use fractional Adams-Bestward-Moulton method. This is here. 13 and 14 is an 14 is explicit formula to 13 formula, and 13 is the fractional Adams-Bestward-Moulton method. Is another method for the predictor-corrector method commonly used to approximate solutions for the fractional differential equation. Similarly, we use the series solution as in 15th equation. This approach is efficient for fractional initial value problems and yields good convergence properties. This is an example, numerical example. If we assume that the alpha is equal to 0.5 is in a fractional order derivative, if our model is here and it is the initial condition. Now we need to use fractional Euler method. We define this method interval 0 and t close interval into endpoints, and our step size is shown as h equal t power n. And we use the Grimold-Letnikov approximation to better understand our numerical example. And we use the iteratively solve step to step. For example, I give some information about the summary of k equations, predictor corrective method, and Grimold-Letnikov approximation to step to better understand our new example. And this type is about the initial volley problem for fractional differential equations. And similarly, these differential equations involving the Caputo derivative and initial volley problem. And it is typically structured as follows. And y of 0 equal y sub 0 is the initial conditions in this differential equation. In cases with higher order fractional derivatives, for example, q greater than 1, our initial conditions extend as follows here. And we need to know where n is the smallest integer greater than q. And y sub 0 and y sub 0 and n are constant specifying the starting state in this part. And boundary conditions, Dirichlet boundary condition and Neumann boundary condition are given to detailed initial volley problem for fractional differential equations. And we need to say it specifies fixed volleys at the boundary conditions to better understand Dirichlet boundary condition. If we give an example, if y represents temperature, a Dirichlet boundary condition might fix the temperature at the ends of a rod, such as this model. And Dirichlet boundary condition and Neumann boundary condition play important role in partial differential equations area in applied mathematics. And Neumann boundary condition asks it specifies fixed derivatives, flux or gradient at the boundaries. For example, if y represents temperature, a Neumann condition could set the heat flux at the boundary according to this here. And this is another results example to numerical results approach predictive corrective scheme. And the generate numerical results to predictor corrective method for fractional differential equations is often employed as it efficiently balances computational accuracy and complexity. And this is the numerical example of our problem. And y0 equal 1 is the initial volley problem to better understand these numerical results, predicted corrective method. And initially we give predictor step, for example, fractional Euler predictor. But we need to say h is the step size and p sub j are weights dependent on the discretization schema. And corrector step, another step to understand our numerical results. This is the improved estimation. And this type is the prediction of our model. And our numerical results was calculated with Python program. And if we assume that h is equals 0.1, our approximation is here according to time with y of t function in a correct predictor step. And this is the fractional decay process model. And this is the fractional decay predictor corrector method according to the step. This is the simulation of the d power q y of t function equal minus lambda y of t function. And this is the MATLAB code simulates a fractional differential equations of the form. We use the q equal 0.7 and lambda is equal 1. If our initial volley condition y of 0 equal 1 and step size equal 0.1, our simulation results was obtained is here according to the fractional decay model. And blue line is the behavior of the solution. And this part is about the existence and uniqueness theorems for fractional differential equations. I gave these theorems previous chapter, previous simulation. But this theorems is very important to fixed point, for example, f of x equal x in fractional differential equations. And Banach fixed point theorem is used to interpretation of the theoretical framework, because one of the most commonly used theorems for existence and uniqueness is Banach's fixed point theorem, which states if x and t is a complete matrix spaces and f x to x is a contraction mapping. For example, C is between 0 and 1, such that the f of x and f of y less than or equal C times the x and y, and x and y is defined and x set. Then f has a unique fixed point in x. And comparison principle can be used as an example of the fractional differential equation. For example, if we consider d power alpha y of t equal f t y function and d power alpha z of t equal g of t and z function, be two fractional differential equations. And if we consider f less than or equal g function for all y in region of interest and v of 0 less than or equal z of 0, then it can be shown that y of t less than or equal z of t function for all t is greater than or equal 0. This principle is instrumental in studying the boundedness and stability of solutions in fractional differential equation. This is another method of the fractional differential equation. Similarly, we use the existence and uniqueness solutions to our model d power alpha y of t equal f t and y of t. But we need to know Lipschitz condition to better understand existence and uniqueness solutions of our fractional differential equation model. And conditions of for application, I gave some informations about continuity of ft of a y function, because f must be continuous in its arguments over the domain of interest. And Lipschitz condition were given places in this part, because the function f must satisfy the Lipschitz condition in y, ensuring that small changes in y lead to proportionally small changes in fty function. This condition is essential for applying Banach's fixed point theorem. And other information is about the implications of the results on stability and convergence. And we use the stability with mythic letter stability criterion. For example, if our model d power alpha y of t equal minus lambda y of t function and with lambda is positive, our solution is here. And E is the mythic letter function as defined as is here. And we know the lambda is a constant of this stability criterion and in this fractional differential equation. And we need to use the convergence of numerical methods. For example, theorem for the predictor corrector method for giving a fractional differential equation d power alpha y of t equal f t y function. For example, this example d power 0.5 y of t equal minus 2 y of t function, we will solve the equation analytically using the mythic letter function and provide a numerical approximation using the predictor corrector method, explain how to implement the numerical solution in Python, including the necessary simulation code. We use the step-to-step corrector method. We use alpha is equal 0.5 and we use the 2 instead of lambda, constant of this equation. We use the step-to-step according to this rule. And we gave mythic letter function to this equation, and we use the predictor corrector method to obtain approach for solving fractional differential equations numerically. And the fractional Adams-Spencer Moulton predictor corrector method are be able to use to simulate and show this problem. But I used only these analytical solutions of the mythic letter function. I did not need to Adams-Spencer Moulton predictor corrector method. It is an alternative method to be understood. And I used several solution step to step. This is the simulation of my example. T power 0.5 y of t equal minus 2 y of t. And orange line is the numerical solution, predictor corrector. And piecewise blue line is the analytical solution, mythic letter simulation. Similarly, we calculate the Python program simulation to interpretation of the solutions of the fractional differential equation. This is another solution according to the derivative, fractional derivative. If we consider 0.6, we look at this blue line. And if our derivative are taken different values, our graphical results behavior are different according to the derivative of the fractional differential equations. And in this chapter is about the stability analysis of fractional differential equations. Here, we will perform an in-depth exploration of stability for systems modeled by fractional differential equations, providing detailed mathematical derivations, criteria for stability, and practical examples with simulations. And in the context of fractional differential equations, stability characterizes how solutions behave as time t approaches infinity. We focus on asymptotic stability and Lyapunov stability, which are critical for understanding the dynamics of fractional systems often seen in control and physical applications. And this is asymptotical stable, d power alpha xt and equal f of x of t function are equilibrium point as t approaches infinity. So we use the stability criterion to better understand our problem. And Lyapunov stability can be used for stability analysis of fractional differential equation, but we need to system, and the system is Lyapunov stable. But if for every epsilon is positive, there exists delta is greater than 0, such that x of 0 norm less than delta implies x of t norm less than epsilon for all t greater than or equal 0. This definition does not require the solution to approach 0, but ensures it stays within a bounded region around the equilibrium. This part is about the Lyapunov's direct method. Lyapunov's direct method is another method for analyzing stability. If we look at this chapter, and if you consider v of x is a Lyapunov function, and we say which is positive definite and whose fractional derivative d power alpha v of x of t provides insight into the system's stability. And in Lyapunov function, for stability, we select a scalar function y of x is positive, but x is different from 0, v of 0 is equal 0 in this part. And fractional derivative condition, we say to confirm stability, we need d power alpha v of x of t function less than or equal 0. For example, let v of x equal x power t p of x, where p is a symmetric, positive definite matrix. If our derivative, fractional derivative is different from 0, the system is stable. But according to the fractional derivative condition, and similar if I use this case, but our fractional derivative is 0, this system is unstable according to the information. And eigenvalue analysis of fractional systems is another information about this my presentation. Due to the non-local nature of fractional derivatives, fractional systems use eigenvalue analysis to establish stability. In stability criterion, for a fractional system matrix A with eigenvalues lambda sub I, our system arc I absolute value greater than alpha p over 2, this condition is okay, not problem. But this condition is satisfied, so our system is asymptotically stable. So this criterion reflects the decay behavior of fractional systems and is essential for systems with long memory effects. This chapter is about the mythic letter function stability. It comes from the previous chapter, and I mentioned that this information. So similarly we know that the mythic letter function are very important to use stability of the fractional systems and fractional differential equations. And on the other hand, we need to use eigenvalue condition and eigenvalue calculation to better understand in our example. And I gave this information for my example. to understand stability of a fractional linear system. And this is another example of the damped fractional oscillator. And for example, if our fractional derivative equals 0.7, and if our constant gamma is equal to 1, the system's response simulated according to Python gives us result. And if our derivative is different, our graphical results are different as according to this definition. And applications of asymptotic analysis, we can use the overview anomalous diffusion, and we can use case studies demonstrating applications. And similarly, previous chapter preliminaries information about the Riemann-Liouville, Caputo, and Atangana-Boolean fractional operator are necessary to introduce the applications of the asymptotic analysis and stability. And memory effects in physical and biological systems are another information about my presentation. Memory effects arise in many physical and biological systems where the current state of the system is dependent on past states. These effects can be modeled using fractional calculus, where the fractional derivative captures the delayed influence of past events on the present dynamics. For example, biological problem. An example is the modeling of the cellular processes and neurotransmitter release. It can be used in the material sciences. This is an example of the fractional Maxwell model in the material sciences field. And significance of memory in modeling. Memory effects imply that the system's future state is influenced not just by its current state, but also by its past history. Other practical applications across various fields and engineering. And I defined the fractional, proportional, integral derivative controller. Similarly, we need to use asymptotic stable existence and uniqueness and stability results for the fractional, proportional, integral derivative controller. Similarly, this chapter can be used only proportional integral derivative controller besides of the fractional version. And this is our model, and these simulations comes from the proportional integral derivative controller model. And it can be used the finance model. And in financial modeling, fractional derivatives are used to model anomalous diffusion in asset price movements. And this is the fractional Black-Scholes equation. And similarly, existence and uniqueness and stability information can be is necessary to interpretations of finance model with the fractional Black-Scholes equation. And summary and conclusion, I used the key information about the preliminaries and basic information about the fractional calculus, fractional derivatives, fractional integrals as Caputo, Riemann-Liouville, and Atangana-Boolean fractional operators and their properties. And later, I gave information about the existence and uniqueness theorem and stability theorem and alternative methods to numerical parts in my presentation. And especially I mentioned about the application area of the fractional differential equations, for example, short memory principle, anomalous diffusion, and control systems, finance model, and nonlinear systems, and real-world scenarios. And if you want to study on fractional differential equations area, I can give recommendations of the fractional calculus models and numerical methods was prepared by the Professor Dimitri Baleanu, Kai Dietan, Enrico Scalzi, and Joan J. Trigilo. And other sources can be used to learn fractional calculus and real-world problems. This book was worked and prepared by the Gio Tenreiro Machado, Necati Özdemir, and Dimitri Baleanu, who is editors, and series editor Albert Gigilo. And other book can be suggested to better understand fractional order systems and applications and engineering. I want to say artificial intelligence was used in this book. And this book's series editor, Valentina Emilia Balas, who is in professors in Romania, and Dimitri Baleanu and Hemen Duta. And this book series editor by Dimitri Baleanu, Valentina Emilia Balas, and Pravin Agarwal. And this book is beneficial to better understand fractional differential equations, which is prepared by the Professor Abdon Atangan and Seda İret Aras as fractional stochastic differential equations. And I can give suggestions. This book, New Numerical Scheme with Newton Polynomial Theory, Methods, and Applications, prepared by the Professor Abdon Atangan and Seda İret Aras. And other book is important to better understand in this field as Newton's nanotechnology and fractional calculus applications that prepared by Dimitri Baleanu, Ziya Burhanettin Güvenç, Cihat Tenreira Machado. And my presentation was finished. This is my key references for my presentation. That's all. Thanks for listening to me. Thanks for presentation. Okay. Do you have any questions about this?
Thank you for your conversation, teacher Taylan.
Thank you.
Thanks. Can I
Is
stop
there
my
any question?
Can I stop share my screen?
Yes. You can stop.
Okay.
We will be very happy if those who are available will turn on their cameras for take a souvenir photo together. Müsait olanlar eğer kamerasını açarlarsa. Süper olur.
Yayını kapatmamı ister misiniz?
Evet, bitti.
Bir yerde yanlış yazdım.
Tamamdır.
CD, Home, Sinem, Catkin Workspace, Source,